So things I'm going to talk about are the pi zero to gamma gamma and the axion. So you want to learn more about anomalies, which I won't have time to really discuss in any depth. There's an introduction in some lecture notes I gave in Les Ouches in 2009, which are available on the archive, which give a sort of gentle introduction. And then there's, that's from me. And then there's a classic paper that anyone who wants to understand quantum field theory deeply should read. It's a difficult paper, but it is so illuminating. Fujikawa in 1979 showed how anomalies arise from a path integral. And his whole calculation really helps you understand how path integrals work, how anomalies work. The gist of it is that when you do a path integral, and S is P4X Q bar I D slash Q, just a massless fermion. When you make a change of variables, Q goes to Q e to the I alpha, sorry, goes to e to the I alpha gamma 5Q, namely a U1 axial transformation. That is the symmetry of this action. But it's not a symmetry of this action. And that is surprising because you would think that this would pick up one phase and this would pick up the opposite phase, and they can't, or sorry, that these would pick up phases, but normally you would say that if Q goes to UQ, then DQ goes to determinant of UQ. And you would find out that the phases would cancel because gamma 5 is traceless. So determinant of U is equal to e to the trace log U. And because this comes with a e to the plus I alpha for the right-handed ones and e to the minus I alpha, this is too fancy. If you have a plus phase for the right-handed one and a minus phase for the left-handed one, you're integrating over lefts, rights, left bars, right bars, then in each one of these individually, you'd expect the phase to cancel, and then this would be an invariant path integral. But these determinants are determinants of infinite matrices, because it's not just the determinant in Dirac space, but it's the determinant over the whole Hilbert space of fields that you're expanding your Q field in. And because of that, you have to regulate it. When you regulate it, you find that this is not a symmetry. And what is a symmetry, however, is that Q goes to e to the I alpha gamma 5 Q, but at the same time, you have to add a theta got ahead of myself here. Let me just get the notation right. So in QCD, it'd be G strong squared over 32 pi squared times G mu nu A G mu nu A dual. And you first have to put this operator in, and then you find that under the symmetry, you also have to transform theta goes to theta plus alpha. Sorry, theta plus 2 alpha. Theta in QCD is an angle. So theta equals theta plus 2 pi. So physics had better return to where you started when theta equals 2 pi. So that means when alpha equals pi, everything should be the same. The reason why that makes sense is because e to the I pi gamma 5 is minus the unit matrix. And q goes to minus q is what you get when you do a 2 pi rotation in space. So if that wasn't a symmetry by itself, you'd be in trouble. So that's why there's this factor. You can remember this factor too, that q goes to minus q had better be a symmetry of the theory. Okay, so because of this, that means that this transformation is not equal to a symmetry. Furthermore, even if you're talking about QED, where you don't put an operator like this in the Lagrangian because it is a total derivative, you still find that the current is not conserved, that the derivative of the axial current, which is another current associated with this transformation, does not equal 0, but in the absence of masses is equal to e squared over 16 pi squared FF dual. This is for U1 electromagnetism. This is for one flavor. You can see this either from this Jacobian argument, or you can see it from a Feynman diagram. If you put a J mu axial at the corner of a triangle diagram, you get this photons diagram like that. And this gives you when you put a factor of momentum coming in on that vertex, which is the derivative, you find you get a non-zero answer. Now, if that happens for one fermion, then for two flavors, so there was an E here, electric charge. With two flavors, you find that you get an anomaly because if I took the current J axial 3 mu, which is Q bar gamma mu gamma 5 sigma 3 over 2 Q, or Q now equal to up and down. Now the divergence would be d mu j mu 3 axial is equal to, well, for the top, for the up quark, this is a half. That comes in at that vertex there. And then I have 2/3 squared E squared. And then for the down quark, I get minus a half from here. But now I have to put in minus 1/3 squared E squared times FF dual times E squared times 1 over 16 pi squared. Yeah.
The sigma 3 is just an isospin matrix.
Yeah, this is 1 minus 1 times a half. So this is your isospin curve. So this is part of your SU2 cross SU2 symmetry. Okay, so this is 1/2 times 4 minus 1/9 E squared, which is 1/2 times 1/3 times E squared. Have I forgotten something? I took into account the charges here, the charges there, charges there. This is part of the danger of our notation. To make life easier, we don't write all the indices. Does an up quark carry any indices other than spin? I mean, I've taken into account the Dirac structure in doing this diagram, but are there any other indices? What quantum numbers does an up quark carry? Sorry, what?
Color.
Color. There are 3 degenerate colors here. And each of those colors can go around here with exactly the same effect because they all have the same isospin and the same electric charge. So I was off by 3. Which cancels this 3, this third. Oh, this was just a half. Now, that's a weird numerical coincidence that made it possible for this diagram to have been calculated in the 40s before quarks were known and color was known. When I was a CERN summer student, I was a student under Jack Steinberger, who wanted to be a theorist. He was a grad student under Fermi, but he had 2 really smart classmates, Li and Yang, and every time he tried to come up with something interesting, they came up with something far more interesting, and he was very depressed. So Fermi finally told him, why don't you measure the endpoint spectrum of the outgoing electron and muon decay? So that was his thesis. He showed it was 3-body decay, and that sort of validated and helped lead to Fermi's theory. That was his PhD thesis. So he goes to the Institute for Advanced Study as a postdoc. He still wants to be a theorist. His office mate is Freeman Dyson. Freeman Dyson is showing that Schwinger's field theory and Feynman's field theory are the same, which was incredibly complex and advanced, and he felt really stupid having such a smart office mate. And he couldn't think of what to do. And then one day there was a seminar where they were talking about the newly discovered pion, charged pions that had been seen in cosmic ray experiments. And Oppenheimer said, it must be part of an isotriplet. So we need to find the pi zero, but the pi zero is presumably also created in the atmosphere, but it wouldn't reach us because it decays too fast into 2 photons. Can somebody calculate the rate for pi 0 to 2 photons? So Steinberger went to his office and he calculated this diagram, J mu pion, which is the same as that current there, and he put the only charged particle he could think of for putting in there, which is a proton, and then he put 2 photons here. The proton does not have any color. There's no degeneracy factor of 3, and its charges are 1, and it gives you the same answer. So he calculated the anomaly without knowing it was the anomaly, and he freely admitted this. He said it was a fluke. That was the only theoretical calculation. He did that during his stay at the Institute for Advanced Study. Got an assistant professorship at Berkeley. They had a bunch of accelerators no one was using because they had invented a new one that was higher. And then he went on to decided he was an experimentalist and went on to discover about half of the particles in the first few pages of the particle data book, like the omega meson and I think he discovered the sigma hyperon and so on. He went on to win a Nobel Prize later for other work. So anyway, we have this anomaly, and we find that one of the currents, namely this one here, which is part of our SU2 cross SU2 symmetry, is actually not a symmetry. So we have to reflect that in our Carl-Lagrangian somehow. So how do we take this equation and realize that in the Carl-Lagrangian? So we know how to match currents. So let's simplify our Carl-Lagrangian to just focus on the pi zero and only linearize the theory. Let's not look at the higher meson interactions. And in that limit where m quark equals 0, if you have quarks, that also explicitly breaks the symmetry, so there's an extra term here, but we can analyze this in m quark equals 0 limit. So I'm just going to take my parallel Lagrangian to be this. Okay, that's expanding the trace d mu sigma dagger term to quadratic order and throwing away all the mesons other than the pi zero. Now, what is this current in this theory? Well, we know that, let's go back to the sigma for a moment, and I will write it as 2 pi 0 sigma 3 over 2 over f pi. Remember, that just is saying that the meson matrix is equal to pi 0 over 2 minus pi 0 over 2, 0. Or if I'm just doing SU2 cross SU2, it's that. And under this transformation, where the quarks are doing this. Okay, that means that Q right is going to e to the I theta over 2 Q right, and Q left is going to, sorry, times sigma 3. And Q left is going to e to the minus I, sorry, e to the minus I theta over 2 sigma 3 Q left, because that's what gamma 5 does. It's 1 on Q rights, it's minus 1 on Q lefts. So this is our L matrix, and this is our R matrix. So how does sigma transform? Well, sigma goes to L sigma R dagger, which is equal to e to the minus I theta sigma 3 over 2. Then this is our sigma, and then it goes to R dagger on the side, which is another e to the minus I theta sigma 3 over 2. And this is supposed to be equal sigma prime, which is e to the 2I pi 0 prime, sigma 3 over 2. And so we see that pi 0 has gone to pi 0 minus f pi theta. This theta is not supposed to be related to that theta. It's just some arbitrary angle. So if I transform my quarks this way with some arbitrary theta, the pion in the Lagrangian has to transform that way. And now I can do another theorem to compute what the symmetry current is for this. And we find it's just equal to minus f pi d mu pi 0. Because this gives me d mu pi 0 by differentiating the kinetic operator. And this is the variation of the pion is minus f pi. And so if you use this Lagrangian, you find that the divergence of this is minus f pi d squared pi 0, which is 0 by the equations of motion, because that is the equation of motion for this Lagrangian. But we also know that in general, so if we want this to not equal 0, so this is wrong because of the anomaly. So we have to put in some non-invariance in the Lagrangian so that the current is not divergenceless. I'm sorry?
There should be a theta time.
Oh, so you're asking why there's no theta here, or no? Here, yeah. In another term, you don't put in the arbitrary angle as part of delta theta. You do an infinite. You drop off the infinite. You don't want to have your current be dependent on some angle that could be anything, right? So you normalize it by taking out that theta. Just like if you did psi goes to e to the I theta psi, a vector transformation, we say that the Noether current, J mu, is psi bar gamma mu psi with no theta in it, where this is dl d mu psi, and this is delta psi. So we drop the theta and we drop the I. So we need to add something in the Lagrangian that is non-zero. So the full Noether's theorem is that d mu j mu is equal to minus the derivative of the Lagrangian with respect to the pion field times the variation of the pion field. So this would be zero if we had a symmetry. Now we need to add something to Lagrangian so that this is not zero, and not only not zero, but equal to the divergence here. Here. We want to add some new piece to the Lagrangian, which is called delta L, such that when I differentiate it with respect to the pion field and multiply by the variation of the pion field, which is minus f pi, this is equal to what we want, which is e squared over 32 pi squared ff dual. And so that immediately tells us that delta L is equal to minus pi 0 over f pi times e squared over 32 pi squared ff dual. So this has to be added to our Lagrangian in order to match the property of the symmetry currents from the high energy theory. And this gives us pi 0 goes to photon-photon decay. It's not proportional to quark masses. It's not suppressed by that. It's not proportional to derivatives acting on the pi 0. So it's not proportional to the momentum of the pion coming out, at least not from that factor. And so this actually answers a puzzle that people had been facing, which is that the pi 0 was decaying too fast for what a Goldstone boson should have been doing. And the anomaly was the answer. Now, I linearized Lagrangian to make the analysis easy. If you want to go to the full operator you have to add involving sigma fields, it's a mess. In fact, I don't even think there's a closed form for how to include the photon in it. You can only do it in perturbation theory. It involves the Wess-Zumino term. It's really interesting, but I don't want to get into it here. The same will be true for the eta. The eta can also decay into 2 photons. I just focus on the pi 0. But for the eta, you'd look at the hypercharge axial transformation. So I mentioned there would be, you could put down a theta term for QCD, which is theta G strong squared over 32 pi squared times G mu nu A G mu nu A. The A is the color index, summing 1 from 8. And this is CP violating. The reason why you can put this in to QCD and not into QED is because while this is a total derivative, it's a total derivative of a gauge non-invariant current. And you actually find when you integrate, you get a surface term that can be non-zero even if all of your color E and B fields are 0 at infinity. With the photon, if the E and B fields are 0 at infinity, the integral of F dual vanishes over all space. But the integral of GG dual does not have to vanish. So that's the difference between an abelian and non-abelian case. Now, really, I'm going to focus on T violation. The CPT theorem says that if your theory is Lorentz invariant, CPT is a good symmetry. So if it's CP violating, it's also T violating. T violation is actually what people measure. How do you see that it's T violating? So T goes to minus T under T symmetry, X goes to X. Now, it's tempting to say that because there's an, sorry, this is dual, so there's an epsilon tense in there. So it's tempting to say that because there's an epsilon tensor here that has one time index, it must be T violating. But that's a little bit too slick because it's true that while time changes sign and X doesn't, when you look at a covariant derivative, you've got that. And the T transformation is anti-unitary, which means that the I goes to minus I. So that must mean that A0 goes to plus A0 and A vector goes to minus A vector under time reversal. And now you get, because of the epsilon tensor, you're going to have something like D0, A1, D2, A3, something like that. You'll get combinations like this. And so this is odd under T because it's a time derivative. A1 is a spatial gauge field, so it's odd. D2 is a spatial derivative, so it's even. A3 is a spatial gauge field, so it's odd. So the whole thing is -1. So it is T violating, but it's not quite as simple as just saying that the epsilon tensor only has one index. Yeah. Yeah. I don't remember electromagnetism. I do quantum field theory. Right. Okay. So fine. So this part looks like a B. This part looks like an E. And therefore, we've derived that E is even under time reversal and B is odd under time reversal. So what do you measure? The most sensitive measurement is the neutron EDM, electric dipole moment. You've got a neutron here, which is neutral, but it could have some charge distribution, so it can have some electric dipole moment. And it has a spin. Under time reversal, the charge distribution stays the same. But the spin reverses, and so these pictures look different, not related by rotation. So the fact that the direction of the, oops, sorry, this is down. The direction of the electric dipole moment is aligned with the spin here and anti-aligned here says that we can create a scalar object, the electric dipole moment dotted with the spin, which is odd under time reversal. So people measure this, they find it small or zero within errors, and that gives you that theta is less than about 10 to the minus 10, I think. Maybe 9, I don't remember, is it 9? In any case, you'd think it could be anything between 0 and 2 pi, but it's tiny. So that's called the strong CP problem. So two questions. How do you see that theta actually gives you a neutron EDM? And second question is, what do you do about it? So the first one is a Carl-Lagrangian question. And at first, it seems horrible. I've got this operator involving gluons that I have to somehow figure out what it does to my Carl-Lagrangian. But the Carl-Lagrangian is all about quark flavor. It's it doesn't know anything about gluons. How would I possibly figure out how to put this in the Lagrangian? So the answer is we can make life easier for ourselves by using the anomaly to take theta out of the GG dual term by doing a chiral rotation on the quarks. If the quarks are massless, it would just disappear because the kinetic terms are invariant under the chiral transformation. But because we have a mass term, what happens is, and that tells you that theta is not physical if the quark masses are zero. Even one quark mass, zero, theta, there's no strong CP problem. But since there are quark masses, when you do the chiral transformation, the phase reappears in the quark mass becomes complex. So all we have to do is to perform this chiral transformation, put the phase in the mass matrix. We can forget about gluons. We just do our usual matching to the chiral Lagrangian, but now we don't assume that the quark mass matrix is real. So we do Q equals I theta over 2 gamma 5 Q. Sorry, I don't want to. We've got, if I do 3 flavors of quarks, say, let's do 2 flavors. So we will rotate both of them equally. So we have a theta over 4 gamma 5 Q, and then, so if I have e to the I alpha here, then theta goes to theta minus 4 alpha. Because I now have 2 flavors of quarks. Okay, so I take alpha equals theta over 4. Now there's no more G dual term. But Q bar MQ, which is equal to, Q bar R M Q left plus Q bar left M dagger Q right now turns into, well, so we had an e to the I alpha on Q right and e to the I alpha on Q bar left. So this becomes, well, I get a e to the Q left gets an e to the minus alpha. Alpha is theta over 4. Q bar right also gets an e to the minus alpha, which is another theta over 4. So I get e to the I theta over 2 here. Plus Hermitian conjugate. Now, I'm not going to go into the details of how you compute the neutron EDM, but there is a way of coupling the mass matrix, quark mass matrix, to the nucleons that I mentioned just briefly at the end of my lecture yesterday. N transforms with the UU dagger. This operator transforms the UU dagger. Let me put a right bar here and an L there and add the Hermitian conjugate. I'm not putting the left and right because of symmetry transformation properties. Both left and right transform with the same U, but I have to make sure my Lagrangian is Hermitian. So since N bar right and left under Hermitian conjugate goes to N bar left and right, I have to write it out like this. So this has some coupling constant. I'm not going to even talk about the dimensions of that. In normal chiral Lagrangian, where M is real, CMC is equal to M plus I over F pi times the anti-commutator of the pi matrix with the mass matrix plus dot, dot, dot. And so you see that the first term is Hermitian, and it'll look like a mass shift for the nucleons that's proportional to the quark masses. The second term, because of the I, these will come with opposite signs, and so it'll look like a gamma 5 coupling. The nucleons with some M quark. I'm dropping the matrix structure, but this is the general form of the interaction you get. So you get a pseudoscalar Yukawa coupling. Totally normal. However, if I put an e to the minus I theta over 2 in here and e to the plus I theta over 2 here, I'll get this times cos theta. But I will also get something that goes like MQ n bar pi and sine theta. In particular, I'll get an n bar pi 0 n sine theta, which because theta is small, is just proportional to theta. And so what I have is an ordinary Yukawa coupling of the pi 0 to the neutron with no gamma 5. That is CP violating, because pi 0 is CP odd, and n bar n is CP even. So that then gets fed into diagram. Now you have to feed this into diagrams with the photon and try to figure out how it gives you an electric EDM. And that's a complicated calculation. People have done it. And that's how they translate this experiment into this. Yeah.
At tree level, you could have written an EDM operator for neutron by itself, right? With something proportional to theta. And this is the loop level piece, right? The pi exchange with the photon.
No, I've written the Lagrangian and QCD where theta only appears through the quark mass matrix. Okay, so the only way it can enter the chiral Lagrangian is through the quark mass matrix, because that's where the CP violation is in this formulation of QCD. And the mass matrix, we're keeping track of insertions of the mass matrix. We're doing perturbation theory in the mass matrix. We're writing down all possible operators, all possible insertions of the mass matrix to all powers. But if you have an operator with no quark masses in it, it cannot have a CP violating term. And that's a good thing, because QCD would not violate CP if the quark masses were 0. So there can't be an operator coming out of QCD that gives you an EDM for the neutron that is independent of quark masses.
There is an operator that electromagnetic charge as some product of the mass matrix, the charge matrices, and n bar n. That's the matrix.
Oh, okay, sorry. You're asking whether with the quark mass matrix insertion, I could just figure out how to write down neutron EDM, and I presume the answer is yes, because typically these diagrams would need counter terms, so they'll be there also. So you, I think though in this case it's finite, because people do calculate it. I don't think it's I'm not certain, but I think it's a finite process and you don't need the counter term. So that would suggest that such a term is higher order. I don't know the answer. Yeah. I'm sorry?
If I calculate theta term n bar gamma 5 gamma and that matrix element on the lattice and vary the quark masses. Let's say I also go to stable paramount.
Okay, so you're talking about what happens when there are negative quark masses. Yeah. So the one thing you have to be careful of is that we also have this trace M sigma term. Okay, and the sigma field is dynamical. So in principle, this could have destabilized the vacuum. It could have made sigma not equal to 1 in the vacuum. We know that the way we parameterize things, that doesn't happen, because our pion mass squareds were all positive. So positive mass squareds for the pions tells you that your vacuum is at least locally stable. Namely, sigma equals 1 is the ground state. We didn't check that, but I mean, well, we did. We calculated the pion mass squareds. They were all positive. So it was a good ground state. If I rotated the mass by phase, or suppose I just flipped the sign of one of the masses, particularly the down quark mass, say, you'd find that mu plus md, which is m pi squared, now is negative, which means I'm not in the vacuum. Sigma equals 1 is not the right vacuum. It's something else, okay? Well, changing the sign of m would be the same thing as having theta equals pi, because I can get rid of theta equals pi by flipping the sign of the quark, of one quark mass. So there's a trade-off between it really isn't different than what I'm talking about. It's just that we could have said that theta was pi, and the quark masses were positive, as I said before. And then the question is, would you find a neutron EDM? And I don't know the answer about that. So, theta equals pi is something that I know people have talked a lot about, but I haven't followed the literature. It was originally discovered by Dashin, that without knowing anything about GG dual, Dashin's noted that if one of the quark masses had been negative, then the vacuum would have to readjust and it would be CP violent. So I want to get to the last part of this last lecture, which is the ingenious solution offered by Pache and Quinn for solving the strong CP problem. This is a great paper, and it's also very instructive to read in hindsight, because you realize that they understood almost nothing about what they were talking about, but just enough to make a great discovery. Okay? They started with the fact that theta GG dual in an instanton calculation, which is an approximate model, shows that the vacuum energy is minimized at theta equals 0. So they came up with a way of putting in dynamical fields. So they added an extra Higgs field to the standard model, and they found that by changing that the Higgs fields could adjust, changing theta so that it could find its true minimum, which is 0, which is the CP conserving vacuum. Somehow they didn't realize that their vacuum can now oscillate locally, and therefore they're predicting a new particle. So Weinberg and Wilczek jumped on it, and Weinberg called it the Higglet, and Wilczek called it the axon, and Wilczek won. But it's all contained in their original paper. Now, also, because the way they're thinking, they're tying it into the weak interactions. It's an extra Higgs doublet that makes this happen. So what they're doing is their observation was, I want to say their observation was, but they didn't observe this, it's in retrospect, this is what they should have observed, is that we already have an example of a pi 0 coupling to FF dual. We've seen this interaction. This is a function of x. Can we get another field, A of x over FA, axion field over F axion times GG dual? So what are the ingredients to getting this? We had pi 0 was a Goldstone boson for a spontaneously broken symmetry. That's the first step. The second step was that symmetry has an electromagnetic anomaly. So that's our recipe. So we have the axion is the Goldstone boson of some new spontaneously broken U1 symmetry. It's a single Goldstone boson. And we'll call it the Pacheco symmetry. And the second thing is the U1 Pacheco current has a color anomaly. We just have to find particles that carry charges under the U1 Pacheco and color charges so that these are non-zero, such that this triangle diagram algebraically doesn't vanish. So the original model then, they used quarks in this, and they invented a new symmetry in the standard model by adding a new Higgs doublet, which allowed them to rotate quarks independently because they weren't locked together by being coupled to the same Higgs doublet. They had independent Higgs doublets. And the Higgs doublets had to transform into this new symmetry. And then when the Higgs vevs form to give the W and Z mass, they spontaneously break this. And you get a new Goldstone boson that's basically made out of pieces of the new Higgs doublet. And in the Pacheco model, F axion is on the order of the weak scale. Now there's all sorts of fun physics to do with the axion. How would I see it? I happened to be an undergraduate at Stanford at the time that Pacheco and Quinn were at Stanford, and they came up with this idea. And I'm sitting in my thesis, my undergraduate advisor's office, who was Mel Schwartz, and young assistant professor Stuart Friedman walks into the office and says, "Hey, Mel, Roberto's predicting a new, and Helen are predicting a new particle that interacts with ordinary hadrons. And it's very, very light, something like an EV or something." And Mel said, "Nonsense, we would have seen it." And Stuart said, "No, we wouldn't have, because it's suppressed by this factor F axion." And so they went to the blackboard and started talking about how you'd see it. And as I sat there, I watched them invent an experiment where you take a beam, you crash it into junk, and you have a big hill of dirt, and you've created kaons here, and the kaons decay into pi axion. The axion's weakly coupled, so the axions come flying out, okay? And then there's some detector here that allows them to crash and create hadrons again. And the dirt served to screen out all the particles that would be created unless there was a super weakly particle. And very quickly, they designed an experiment and were able to rule out the Pacheco model. In particular, if you take K to pi axion, this is a dramatic decay because it's two-body decay, so the pion's monochromatic with half the kaon mass. It would really stand out. So this gives you a bound F axion has to be less than about 10 to the 6th Jev, much higher than the weak scale. Sorry, what? Yes, greater. Thanks. But it didn't take long for people to go back to this recipe or to extract this recipe from this incredibly complicated, confusing paper and realize that really the rules are very simple. So there's nothing that says this U1 symmetry has to come with the weak interactions or break at the weak scale. You can invent new physics high up that has a particle symmetry with this anomaly. And then F axion can be as big as you want. It's the theorist's delight, you know, experimentalist nightmare. By the way, watching that interaction between Friedman and Schwartz made me decide I wanted to be a theorist. It's sort of strange, you know, you're watching these experimentalists do this great work on the blackboard, but all I could think of is, wow, I want to invent particles too. So let's assume that there is some model, these are pretty easy to construct, where there's some high energy physics, and while this isn't strictly true, I'll assume that the only thing that comes down to our low energy standard model is this g squared over get the normalization. Alpha strong over 4 pi times GG dual, trace GG dual. I might have a factor of 2 wrong there, I'm not certain. But that's the only thing that comes down to us. We add this to the standard model, and that's all we see from the high energy physics. So now, what do we do? Again, you'd say, well, that's horrible. This axion is going to go through gluons, and it's going to mix with the eta and the pi zero and the eta prime and blue balls. Well, we have the trick now that we use for studying how the effect of theta. We can rotate quarks by an axial transformation that depends on the axion field. So instead of theta, we have this. Now the axion appears in 2 different ways. So I'm going to assume that Q transforms, and I'll take Q equals UDS, 3 flavors, and it transforms, and I do a change of basis where this transforms to e to the I axion of x over f axion times this matrix Q times a gamma 5, where Q is Q1, Q2, Q3 down the diagonal on the 3 flavors of quarks. And all I need to remove the axion from this thing is the constraint that trace Q equals a half. Trace Q equals a half because the color normally only cares about the trace of Q because I'm summing this diagram. If I use the current coming from this symmetry, there's a Q here, and when I sum up over the particles, they all have the same color, so I get a trace of Q in the diagram. So you might ask, well, why didn't I just take unit matrix divided by 6? And the answer is going to be clear in a moment why I want to have it be more general at the moment. As long as trace Q is a half, it'll remove the axion from GG dual and put it in the quark mass matrix. So now I've got trace M e to the I have a minus sign, yeah, okay, minus 2I axion of x over f axion times q times sigma in the Lagrangian plus Hermitian conjugate. So now I have figured out how to put the axion in the chiral Lagrangian. There is an extra piece though, because since this is an x-dependent transformation, I also have d mu axion of x over f axion times the q bar gamma 5, gamma mu gamma 5, capital Q, little q interaction in the QCD Lagrangian. This wasn't there when I did a space-time independent transformation, but now I've got this axion derivatively coupled to axial currents. So this will also go to the chiral Lagrangian. I know how to match axial currents on the mesons, how to match it on the baryons. So I'll have information about the coupling of the axion to various particles. But at the moment, I want to focus on this so I can look at the mass matrix and the axion potential. I want to find out what the axion mass is. So now the reason for having a freedom here to choose Q is that if I expand to order A pi, in linear and axion, linear and pion, I will get something that will lead to axion meson mass mixing, where plus lots of other terms. But this is not fun, because that means the axion is not a mass eigenstate in general. So now this is where I'm going to use my freedom to choose Q to automatically make this vanish. And it's easier to figure out than you might guess, because remember that trace of the pion matrix is 0. It's a traceless matrix. So if I can choose Q times M to be proportional to the identity matrix, this will vanish. So I take Q is equal to M inverse over twice trace M inverse. And if I do that, then the axion is a mass eigenstate. So this is 1 over mu, 1 over md, 1 over ms, over twice 1 over mu plus 1 over md plus 1 over ms. And so to a pretty good approximation, since the s is quite a bit heavier, you can forget about the s, put a 0 here and a 0 there, because it's so much heavier than the up and down. And you see that the axion will mainly couple to the up quark and somewhat to the down quark and hardly at all to the strange quark. So now I know what Q is. There's a subtlety, which is that this operator can give you off-diagonal wave function mixing, but you'll find that it comes in at higher order in 1 over f axion squared, and f axion's big, so you can ignore it when looking at the potential. So now you plug this in. If you want the axion mass, you go back to this operator. If I want the axion potential, I go back to this operator and set the pions to 0, and I've got my axion potential, and I know I don't have problems with mass mixing. There are higher order terms where they interact with each other, but we really are not interested in anything that's has inverse powers of f axion higher than 1 power, because f axion is going to be very big, so this is going to be very weakly coupled. So really the interactions between pions and mesons that come from higher order terms in the axion at least are not interesting. So we have to look at, we have a f pi squared, lambda tilde, trace m, e to the I, m inverse over twice trace m times 2a of x over f pi. I guess I had a minus sign, Hermitian conjugate. And now you can expand this in powers of the axion and find out what the axion mass is. If you simplify this, where you take mu equals md equals m bar, you find very quickly that m axion squared, so this is minus 1/2 m axion squared plus dot, dot, dot. And that's the definition of the axion mass. So you compare these and you're going to find that m axion squared is equal to m pi squared, f pi squared over f axion squared. The m pi squared comes from trading lambda tilde times m bar as being m pi over 2, m pi squared over 2. So now you start, people get really interested in putting bounds, more stringent bounds on f axion. More stringent one, the k pi axion is the most stringent accelerator bound, but people realize that in stars, particularly supernovas, you have a process where, say, a proton can be struck by a photon, get knocked, and emit an axion. Okay, and what this has done is it normally you'd say, well, that's just part of the equilibration and temperature in the star. But this axion being very weakly coupled, F axion being big, is able to sail straight out of the star without interacting again. And so it becomes a way to rapidly cool the star. And if you cool a star, strangely enough, the star gets hotter, right? The faster you cool the star, the more it compresses. The hotter it gets, the faster it burns out, and its lifetime gets very short. Stars have negative specific heat. It's very bizarre. So you know that supernovas last longer than a year, right? That tells you that F axion is bigger than 10 to the 10 GeV. Then it turns out that when F axion is on the order of 10 to the 12 GeV, there are enough relic axions to equal cold dark matter at the right density to explain structure. So this is sort of an exciting number for experimentalists then. You turn this, you look at, you plug that into here, and that implies that M axion is on the order of 10 to the minus 5 electron volts. You then exploit the fact that I hadn't written here, is that when I do this performance on the quark, there's also an electromagnetic anomaly. So I generate an A of X over F axion times FF dual when I do this rotation. And so the axion has a coupling to 2 photons. So you have an axion coming down from outer space as part of the dark matter. You put it into a cavity, this experiment was invented by Sikivi. You've got a large B field in here. So this provides a photon which strikes the axion, and the axion then can produce an E photon. And you look for the excitation of your waveguide due to this photon, and they are probing this range here, looking for axions coming in from outer space. One of the experiments that is being done on this is at the University of Washington, and the professor doing it said that he's got an amplifier at the quantum limit that is sensitive enough that if there was no background noise, you could pick up a cell phone from Mars using it. Okay, so that's the end of my lectures. I think I just give you a tiny little taste of ways to use things. There are many other applications for chiral Lagrangians, even beyond looking at mesons. As I said, if you look at dense quark matter, you have color flavor lock phase. It has excitations. You can use a chiral Lagrangian to study those. I've used it to study KN condensation in dense matter. I've used it to study composite Higgs models where I've got a strong interaction that's above the weak interactions, and it creates its own chiral Lagrangian. Many uses for this, many uses for all the different techniques of effective field theory. So if you have a problem you can't understand, one of the first things I ever say is, let's see, is there an effective field theory tool that helps me understand this? Hope it helps. Thanks.